In this video, we're going to look at matrix multiplication. Before we start multiplying out matrices, let's first look at how do we know when two matrices are going to multiply out. Say you're given two matrices, A and B. They can be multiplied if and only if the number of columns in matrix A equals the number of rows in matrix B. So if matrix A has dimensions of n by n and matrix B has dimensions n by p, then the product between A and B has dimensions m by p. So looking at a few examples here, if we use the following matrices, let's determine if the product is defined. If we know that it is defined, then let's give the dimensions of that product. So we'll look at these 5 matrices. We have A, B, C, D, and E. The first product we're going to look at is what's the product between A and D? Well, first we need to look at the dimensions of matrix A. We need to look at the dimensions of matrix D. The dimensions of A has 4 rows by 3 columns. Matrix D has 3 rows by 1 column. What you need to be careful with is, do the numbers closest to each other? Do the columns from the first matrix match the rows from the second matrix? If it does, then the dimensions of your new matrix will be the outside 2 numbers. So this will be a 4 by 1 matrix. Here's a second example. Let's take matrix E multiplied by matrix B. Again, we need to check the dimensions of the matrices first. For E, there are 5 rows with 2 columns. In matrix B, we have 1 row with 5 columns. What you should notice is that the columns and the rows do not match in this particular setup here, so this is not possible. There cannot be a product between these 2 matrices. Let's do a third example. Let's take matrix E multiplied by matrix C. Again, let's identify the dimensions. Again, 5 by 2 for E is the dimensions of that matrix, and then for C there are 2 rows by 4 columns. This time the rows match the columns, so the dimensions should be a 5 by 4 matrix, and that's what we will get out of this when we do the matrix multiplication. So now we know how to find the new dimensions of a matrix product. Let's go in and let's define how to find a product of matrices. So how do we multiply matrices? If you get one matrix A and a second matrix B, then the product of A times B is equal to the following matrix. Another way that you can think of this is, if I want to take the top row of matrix A, multiply it by the left column of matrix B, you will have a new number that goes in the top left of your matrix. If you take the top row, multiply it by the right column, then you'll have a new number in the top right-hand corner of your new matrix. If you take the bottom row, multiply it by the left column, you'll have a new bottom left number in your matrix. And then likewise, if you take the bottom row and multiply it by the right column, you'll have a new number in the bottom right-hand corner of your matrix. We'll always multiply 2 numbers together and then add it with the next product. And this rule follows for any matrix that you're able to take the product of, so it doesn't have to be just 2 by 2 matrices. And to be able to show this, we're going to look through some examples. So let's find the product if it's possible. We're going to take 2 by 2 matrices and we're going to multiply them together. So I'll always double check to make sure, do my columns in the first matrix match the rows in the second matrix? And I do want to point out too, when we do matrix multiplication, we'll always go from left to right. So columns and rows match up. We should end up getting a 2 by 2 matrix when we multiply this out. So I'll go ahead and take the top row, multiply by the left column, whatever that product in sum gives us, we'll get a new number in the top left-hand corner of our matrix. So when we take negative 4 times 6, we get negative 24. Take negative 9 times 5, we get the positive 45 that's up here. That'll be the new upper left-hand corner number. So when we simplify, we get 21. Then we'll take the top and then the right column. That'll give us a new number in the top right-hand corner. So negative 4 times 1 gives us 1. Negative 9 times 4 gives us negative 36. So we'll subtract those two numbers, which gives us 32. And then we'll continue this with the bottom left. That'll give us a new number in the bottom left-hand corner. 3 times 6 gives us 18. Negative 2 times negative 5 gives us positive 10. 18 plus 10 gives us 28. And then finishing out the last, 3 times negative 1 gives us negative 3. Negative 2 times 4 gives us negative 8. Negative 3 and negative 8 will give us negative 11. So there's our new 2 by 2 matrices when we multiply the orange and the pink matrices together. So that was multiplication of keeping the dimensions the same. Let's take a look at where our matrices will change with its dimensions. So first we check the dimensions. Make sure that our columns and rows match. We have a 2 by 3 matrix multiplied by a 3 by 1, so we should end up getting a 2 by 1 matrix for its product. So then we'll take the top row multiplied by the only column. This will be a number that goes in the top of this new matrix. When we do this, we will get 42 plus 8. 42 comes from the negative 7 times the negative 6. The 8 comes from 2 times 4. And the negative 11 times the negative 3 gives us that positive 33 that you see in the matrix. Combine those numbers together and we get 83. We will do this again by taking the bottom row times our column, and that will give us our new number that goes in the bottom of our product matrix. So 3 times negative 6 gives us the negative 18 that you see. Negative 5 times the 4 gives us the negative 20 that you see. And then negative 2 times the negative 3 gives us the plus 6. And when we combine that up, we get negative 32. So there is the matrix of this product. So we took two matrices that had bigger dimensions, and whenever we multiplied it, we got a much smaller matrix with its dimensions. We're going to take a look at one more example. We check our dimensions from these matrices. We have a 3 by 1 matrix multiplied by a 1 by 3 matrix. Both of these matrices look fairly small, but when we multiply it out, we're going to end up getting a bigger matrix, a 3 by 3 matrix. When we take our multiplication of this, we'll take the top row times the left column. So this will be the top left number in our matrix. 14 times negative 1 is negative 14. We will continue with this. The top number times the middle. This will be our top middle number. 14 times 9 gives us 126. We will take the top number once again multiplied by the right column. That'll be the top right number in our matrix. 14 times 5 will give us 70. And we will move on to the next number in our first matrices. So then our row number here, negative 2 times negative 1, that will be the middle left number in our matrix. Negative 2 times negative 1 gives us 2. We will continue with doing negative 2 times 9 gives us negative 18. Then negative 2 times 5 gives us negative 10. Move on to the third and final row. Negative 6 times negative 1 gives us 6. And then negative 54. And then finally, negative 30. So we took two smaller matrices, multiplied it together, and their product ends up being a much bigger matrix. Here we got a 3 by 3. So the last thing I'd like to talk about is that this should pose a big question for you. Is matrix multiplication, is it commutative? Does it have that really nice commutative property that our real numbers have? Or in other words, if I take matrix A and multiply it by B, will that be equal to matrix B times A? Let's see if we can do this with an example. Suppose that we have matrix A, 3, 4, negative 1, 8, and matrix B, negative 2, 7, 10, and 6. Let's go ahead and multiply these out. Let's start with A times B. That means the red matrix times the blue matrix. If we go through our matrix multiplication rules, we get negative 6 minus 7 in the top left, 30 minus 6 in the top right, negative 8 plus 56 in the bottom left, and 40 plus 48 in the bottom right. Combine And this matrix turns out to give you negative 13, 48, 24, and 84. Let's save that and come back to it. Let's do B times A now. So instead of red times blue, we're going to do blue times red. Go through our rule because we have to multiply matrices from the left to right direction. Take negative 2 and 10 and multiply and add with the 3 and the 4. Gives us 6, negative 6 plus 40. And then the top right, we get 2 plus 80. And the bottom left, we will get 21 plus 24. And the bottom right, negative 7 plus 48, which will give us this matrices. 34, 45, 82, and 41, which goes to show these two matrices are not equal. Although they have the same exact dimensions, the numbers in the corresponding spots of these matrices are not the exact same numbers. So therefore, AB does not equal BA. Matrix multiplication is not commutative. It does not have that nice property that our real numbers have. So there you go. That's